I'm Dr. Jeremy Kepner. This is Dr. Hayden Jananton. We have many roles at MIT. Our principal one is at Lincoln Laboratory, and we're both part of the supercomputing center there. So we get the opportunity to work with everyone at MIT, helping them do mathematics on big data and a lot of machine learning. And so the lecture we're talking about today is sort of represents sort of a collection of insights and mathematical insights we've developed over the last decade or so, working with people across a really large range of problems. And I was saying earlier, we of course have lectured on this extensively. We have a textbook which we will, pass around and people can take a look at. We have online lectures, very similar to this one. So to kind of honor the fact that we're all here together at this moment in time, and this will never happen again, right? This group of people, we try and make this a little bit more special than us just going up and giving the same lecture that you pretty much can find on YouTube. So we're going to try and experiment here with improv mathematics. So I'm going to give a little bit of an introduction to some of the topics that we'll be covering or can cover in a sort of hopefully a stimulating way. And then while you're watching that, you should write down, like, what do you want to know? It's almost like an Ask Me Anything, but kind of within this topic space, what's interesting to you? What would you like to learn more about? And then we'll collect those, and we will huddle up a little bit, and then try and organize a lecture based on what it is you've told us. So we provided you all with pencil and paper, because we don't know if students actually still have those things anymore, but we thought that would be fun to deal with ancient technology. And so I'm going to give a few sort of introductory remarks. My chalkboard skills are bad, so I apologize that you'll have to bear with that. Hayden's are much better, but I think both of us are a little bit out of practice. So let me just sort of start this. Also, I'm left-handed, and our writing system is designed for right-handers, so it's a natural disadvantage. So let's see here. So we're going to be talking about math, right? So I got that right. Of big data and machine learning. So let's go from right to left here a little bit. So obviously machine learning, and I'm just going to kind of throw out some of the buzzwords that people affiliate with that. So, DNNs, deep neural networks, of course, are kind of the technological basis for a lot of machine learning, if not like 99% of it. And of course, AI, they play a huge role in that. And of course, everyone today is all excited about things like, ChatGPT. And, of course, Microsoft is a huge part of that, and other companies. Let me spell that correctly. Oh, see, I know. See, when you have the clean whiteboard and then you have to do the erase, it just ruins it, doesn't it? Because it's like, I think sometimes professors come in and like pre-chalk their boards a little bit, right? So, yeah, Microsoft. Right. So these are just some thoughts that hopefully can stimulate, what you might want to write down. Let's talk about big data. So, that kind of just began with spreadsheets. Your Microsoft Excel spreadsheet. That can be big data, Databases. So if you do financial transactions, or other types of things, those are very important. And things like that. Obviously, just the internet, right, is kind of the original source of all things big data, right? The concept of big data didn't really begin until the internet the internet as part of its operation just naturally collects and records huge volumes of data. And so the whole field of big data was a natural part of that. And then searching the internet was a big thing. Now, most of you probably don't remember what it was like the internet before Google. There were search engines. They would return the web page that had the most instances of the word that you typed. So there are web pages that just had the word like dog 1 million times on them, because that would be the top of the search engine. There were books of the internet. Like, you could buy printed books or encyclopedias that would list in them, in topical organization, web pages you could go and visit to learn more about topics, right? And so Google search played an important role in making the internet useful. So search, and then, of course, things like Google, were very important there. And then on the math side, all of this is covered. There are mathematical motivators and drivers of all of this stuff. And, we've written a few books over the years on these topics, and you will find many of them if you see and look in the background on the shelves of many big tech pioneers. You'll see our books there, and we've certainly played a large role in kind of defining the mathematical foundations of many of these things. So, I would say matrices are a huge part of that. The Google search engine algorithm was originally formulated 25 years ago. It's just the eigenvector of the first eigenvector of a matrix. It took a month to compute, right? In fact, Google search used to update every month, and you could tell exactly when it happened because it took them that long to compute it. But matrices, the whole internet, we can represent as graphs. And then there's deeper mathematical structures here. So these are just some topics that sort of define the space. And so I'll give you kind of a minute or so to kind of write down what you're curious about. And then we'll see if we can build a lecture that's based on what you're interested in, based on that top. Or it'll fail miserably, and in which case Fortunately, though, I'm going to only speak for 45 minutes, and Hayden has some more traditional, safer mathematical material that will get into kind of proofs and theorems and things like that. So it's not guaranteed to be 100% a disaster. So with that, just go ahead and write, and we'll collect in about a minute or so. So let's talk about some of the basic data structural elements. People were asking. Some of the questions have to do with that. And so So this is a matrix, right? It's 3 by 3, has 3 rows, 3 columns, and we're going to say it has essentially 5 non-zero values. You'll just see I put a dot for a non-zero value. You'd see in my world we only really care about the presence or non-presence of an element. We often deal with these matrices are often what we call sparse. The term sparse just means that a significant fraction of the entries are 0. And that's really nice because we can implement these without storing those. And the reason we don't need to store the zeros is because when we do math on 0, we know what the answer is, right? If we add 0 to something, well, we know what the answer is. And if we multiply 0 by something, we know what the answer is. And for those mathematical reasons, why we don't need to store the non-zero entries. Now, another thing that we can do here, right, is this matrix can also be represented as a graph. Likewise, a graph can be used to represent a matrix. So for instance, let's say I had 3 computers on the internet. There was a time when there were only 3 computers on the internet. And I think those computers were here in Cambridge. So, but if we have 3 computers on the internet, right? And this is mapping communications between them, right? So if this is the start of a message, and this is the end, right? Well, we're saying we have a communication from computer number 1. Let's call this computer number 1, 2, 3, and computer number 1. Or even more importantly, let's move ahead from when there were only 3 computers on the internet to like when the World Wide Web, became available. Let's say these computers are running web servers, and they had web pages, and they were linking to each other. They were pointing at each other. Or even more modern, because I may still have data you, let's say this was Instagram, right? And there were 3 people on Instagram, and this shows like who's following who on Instagram. It's the same concept, right? Whether it was just how computers link on the internet, web pages, Instagram, it's the same idea. And so what would this represent? Well, this would represent computer or web page or person, talking to themselves, right? 1 to 1, all right? So you can have a web page that links back to itself. Totally can do that. I don't know if you can follow yourself on Instagram, but maybe you can. So it's an easy way to get a lot of followers, I would imagine. So that, and typically we would often draw an arrow connecting that. So sometimes we draw a little arrow like that. That sometimes is called a self-loop, graph term there. And the way I've drawn this, it turns out, accidentally, they all have self-loops, right? So all these pages, which is true of the web, by the way. Most web pages have links to other parts, that are on the same computer. That's a pretty standard thing. And then likewise, this just shows, okay, number 1 is talking to 3. So that means we have a connection here. Draw an arrow there. And then we have, let's see here, and then we have 3 is talking to 1, right? Right there. So, and then 2 is only talking to itself, right? This is sometimes called an isolated vertex in graph theory, right? It's a rather unusual graph, but and certainly not the kind of graph we typically study in graph theory because it's sort of uninteresting. But I will say, very typical of the real world. The real world tends to not have too many topologically interesting graphs with like nice shapes and other types of things in. It tends to be lots of self-links, things just pointing themselves, and then huge amounts of communication between, important vertices, right? If you looked at things on the internet, like the links between Microsoft and Google would be, and the amount of interactions going there would be gigantic, right? Certainly much more than any computer UI run. So although not something we typically study, it is something that is very representative of the real world. So operationally, let's say we want to do math on this kind of data, right? Well, we have to store it in something. And in order for to store it, we typically would put it in something called a database. So a database is a computer system or computer technology that essentially stores records that can then be looked up. And for instance, search is essentially something that is, it's stored in a database. And a typical database, right, will have a table that will look just like this, and they're called tables. And they will have rows, right, with identifiers for each row. Typically, every single time a new record comes along, it will add a row. And then columns that, contain what is in the record. Now, traditionally, you might think of these records are often used for, say, financial transactions, where the row is a purchase, and the column contains, one column might be like the product that was purchased, and the other column, another column might be who did the purchase and their credit card number and things like that. That kind of database for financial transaction, what's really nice about it is that the number of columns tend to be very finite. 5, 10, 20 columns, maybe 100 columns if you get large. And they're very predictable. They're very much designed in advance. When you design such technologies, you know what you want in your records. And so when you build those kind of databases, the technology for storing them and using them is very much based on this fact that the columns tend to be fairly fixed over time. And knowing that, you can do a lot of things to make it perform really well. Such a database is very bad, or suboptimal, not very bad, suboptimal for storing data that's going to deal with things like I want to analyze all the people on Instagram and who they're following and things like that. And so to overcome this problem, right, so these traditional databases that are often sometimes associated with something called, if I write these letters, I don't know if you've ever heard them, it's called SQL. And that stands for System Query Language. It is a standard for designing these types of traditional databases, which are often done for financial transactions and other things. Every single time you do a financial transaction, you are probably working and interacting with an SQL database. And there are many companies that make them. The most well-known is probably a company called Oracle, which you may have heard of, but that's kind of how they make their money, is doing that. So to address this problem that these databases weren't so good at dealing with searching dynamic things like the internet, a new type of database was developed, right? And it was called NoSQL, or sometimes this is called SQL. Now, this is not meant to be like we are against, it's not like SQL with a line through it. This actually stands for not only SQL. It means SQL is great, but if we kind of enhance it or add some things to it, it can do this problem better. And the kind of most famous one of these was produced by Google about 20 years ago, and it was for storing a table like this that stored every single web page on the internet. So the rows were every web page, and the columns were every web page that each web page was pointing to. And this is sometimes called, when we're referring to this, called an adjacency matrix or an adjacency array. And so they created a new type of database called Google Bigtable. That was very good at storing this kind of information. And the main thing that it was good at was storing what we call very sparse tables, right? If, let's say I have 1 billion web pages, right? Well, a typical web page, and if I only store the things it's linking to that are not itself, might only link to tens or hundreds of other web pages, right? So essentially we have 1 billion rows and 1 billion columns, but in any given row we might only have 100 entries. Well, it wouldn't make any sense to store the 1 billion minus 100 empty entries. So they designed this technology to be specifically good at that, what we call sparse problem. And so, furthermore, it was also very good at being dynamic. you could add rows and columns, and it didn't care, right? And so this is kind of how they kind of did it to get the technology going. Now, how do I do search, right, in this context? That's the question. Like, this is sometimes in Google, this is just called the algorithm, right? It's like the $1 trillion algorithm that, you know, Sergey Brin and Larry Page developed while they were grad students at Stanford, right? They also developed this technology for going and scraping the internet, creating these kind of technologies for storing it. But how we were going to do better than the kind of search I described before, which is just like, well, show me a web page with the most popular word. So what they realized, something that they just tried a lot of things, and something that worked was that if I do a search for a word like dog, and I get all the web pages that contain dog in them, how do I rank them? How do I present them to the user in that standard Google interface that we see today, which is an ordered list, you know, with the things that they think are most relevant first and going on down? And what they discovered is that if you took the first eigenvector of this matrix and used that value, and it's slightly modified, but it's essentially that produced a really good sorting of the things. And the sort of statistical basis of that thought was that eigenvector kind of represents, if you just randomly started somewhere on the internet and just started following links around and wanted to answer the question, well, how much time would I end up at any one place? The first eigenvector is an approximation of where you would end up the most. So the theory ended up being, well, important pages are linked to by other important pages. So if you have a page that you know, has about dogs, and some other really important page links to you, well, then you are now an authoritative source of dogs. Now, in the early days of the internet, where almost all the content was just stuff being put out by universities, this worked really well. But the moment it became commercially important to be at the top of a search list, which of course you can do just by paying Google, like you can go and say, hey, certain keywords, if I pay enough, you'll put me in that ad section, right? But if you also just wanted to be, then people started playing games with their web pages to sort of game this algorithm. So the current Google algorithm, search algorithm, is now, of course, vastly more sophisticated and does a lot more complicated things than that. And in fact, my understanding is that, you know, one of the most important things when you do a Google search is the auto-completion feature. You type a word and it starts guessing what your next word is, right? And that technology, which is now based on neural networks, was pioneered right here at MIT by some professors here, too. So, you know, there's been a lot of influence. A lot of the ideas here at MIT have had a big impact on that. So that's kind of like, I think I've answered a few people's questions. This is sort of the story. Let's talk about some of the mathematics, though, some of the issues that we have to deal with, right? Because I started out with a nice 3x3 matrix, and, you know, we kind of understand the math of that. I mean, it's something we teach in 10th grade, sort of in a tortured way for 1 week. You're going on doing algebra, and then we sort of say, okay, now do the determinant of a 3x3 matrix, because that's just really painful, and then you'll do that for a week, and then you go on to doing your other stuff. But that kind of, the matrix view of math has some limitations when we're trying to solve these kind of problems, right? The main thing is one way to view what a matrix is, right? And let's say I have a matrix A, right? And it's viewed as a mapping between sets I and J to a set of values, right? And in this case, you know, I is the set 1 2, 3, and j is the same thing in this case. They're both that, right? And then the values might be the real numbers, right? Well, the internet, like, we don't just assign a matrix number to every web page on the internet. It doesn't really work. That's not how it's these things called URLs that are big strings, right? They can be very, very long, right? You know, www.mit.edu. Those are sort of the labels that we use for web pages, right? And the values themselves, like is that the number of links? Maybe when we want it to be what the keywords were or something else. So we would like to be able to do the kind of math we do on matrices, right? But we want to do it with this new type of data. And that's essentially the work that Hayden and I have done and what this lecture is about, and what we talk at great length in our book, was extending the idea of matrices to encompass this new type of data. And it turns out it took a lot of work to figure it out, but it's quite simple, right? We essentially say that instead of, oh, that looks just lovely. We now say that I, is sometimes uses, S, $sign or whatever. We'll say this is any strict, totally ordered set. So that just means I have a set of things and I can sort them. And the reason we do that is because sortable lists, we can find things fast, right? If I give you a sorted list, I can, in a very simple number of steps, get to any one element of the list pretty quickly, right? And then likewise, the values we say are the same thing. This allows us to encompass things like words and strings, right? So now my matrix, which we will call an associative array, matrices are a formal subset of it because integers are strict totally orderable sets, so are the real numbers, right? This allows us to encompass this whole new world of the internet, whether it be web pages or Instagram pages or anything like that. And we can also do matrix math on them. And you're like, well, how can you possibly do matrix math on strings? So let's walk through some of those ideas and some of the big ideas there. So it's sort of, we talked about 10th grade math. Now we're going to talk about elementary school math, right? So we're going to go back, right? So we're going to start with, 2 times 3 plus 4, right? So hopefully I haven't lost anybody. We're all good with this, right? Is equal to 2 times 3 plus 2 times 4, right? So does anyone remember what property I've just illustrated here? The distributive property, right? Yes. So hopefully the internet got that the MIT students recognize the distributive property. So this is good, right? So now I would argue this is really important. If multiplication does not distribute over addition, math sort of stops 100,000 years ago, right? Think about it. It's like, okay, I have, a set of 3, I have 3 cows and 4 cows, and I want to double that. And that's not the same of doubling the set of 3 and doubling 4, right? People are like, what is this math thing you're talking about? This is useless, right? So I'd argue the distributive property is really, really, really important. In addition, no pun intended, in addition, the things we might want to do this distribute over are much broader than just traditional arithmetic, right? We want to, this covers our traditional matrices where we have 2s and 3s and 4s, right? Those are all consistent with those values. But what if I want to do something that's sort of more general? What if I want to do this kind of arithmetic over over more general things. So if you will allow me, right, I'm going to make a change to this equation, and I'm going to put circles around these operations, right? And of course, we know in math class, now we're doing serious math, right? Because we put circles around our pluses and multiplications. So now it's advanced math. Before, if it's just regular, right? But we put a circle around it, and it's really... And the reason I'm going to do this is I'm going to play some games with these operations. So obviously, you know, I can just say, you know, multiplication equals traditional arithmetic multiplication, and addition equals traditional regular addition. And Hayden will get into some of the details, but this sort of pair of operations, which defines a lot of structures in mathematics, is clearly the one that we work with a lot, right? It's the most popular pair. But there are other pairs of operations that we can pull upon that will also satisfy this distributive property. So, for instance, you know, we can do, I guess I got these sort of in the wrong order, but let's see. We can do union, oops, let me do it the other way. Right. You can do intersection and union. Well, now I can work on strings, can't I? Right, because I can do that. And then we could also do, this is sort of a funny one, plus and max. That works on real numbers, but this is actually very important in a lot of areas like deep neural networks, and we'll get to things like that. So by recognizing that we can generalize addition and multiplication, this allows us to cover more diverse data and still use the same math that we really enjoy to deal with the kinds of modern problems they would want to deal with in dealing with all the big data on the internet. So I think I covered those first two pieces pretty well. And I think I covered, did it Google? Yep, a lot of people ask Google. Yes, so first eigenvector of this adjacency matrix to the internet, slightly modified a little bit, is called PageRank. That is what Google called its original search engine algorithm. Okay. So, all right, so how computations on large graphs are done efficiently. I think we talked about. It's all about sparsity and not storing the non-zeros. So one of the really interesting things, though, about the kind of data that we see on the internet, and I'd already talked about this, like that the kinds of topological structures we often study in graph theory don't tend to be represented or seen in this kind of data. The thing we do see a lot of over and over and over again is things that look like this. These are sometimes called star graphs. Sometimes this will be called a supernode, right? This might be Google or Microsoft or some really popular entity, right? And these are us, right? Or, you know, we may have like no connections to anywhere else, right? I mean, if you just create an Instagram account, you have no followers, right? So, except probably Instagram itself, right? Or maybe it gives you one, you know, to start. And you'll have something like that. So it turns out the internet and a large fraction of things that have to do with human activities produce graphs that look like this. And a way to characterize this type of graph is to look at the statistical distribution of each of the vertices. So we'll create a histogram here, right? So we have one vertex with 1, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5, 6, 7, right? I can count to 7. 7 connections, right? So if I have my x-axis is 7, right? 8? All right. 8. I'll trust you, Hayden. So, and then we have 1 here. So we have a point here, right? So we have one vertex with 8 connections. So the x-axis here is the number of connections the vertex has, right? And then we have eight vertices with 1 connection. So and if we were to scale this up and look at the entire internet, and we sort of bucketed these things by powers of 2, like 2, 4, ... sort of logarithm, you would see that you would get points that sort of fall along a line here. And sometimes we'll call this value the degree, right? And we can look at the probability of having a vertex having this many connections or having a degree of this thing. And it often essentially is proportional to 1 over d to the alpha, where alpha is typically, you know, between 1 and, say, 3. Now, this kind of statistical distribution is sometimes called a heavy-tailed distribution. You probably have never studied them in all the statistics courses you've seen, even though they're extremely common. And in fact, many of today's most important problems, anything to do with the internet, anything to do with natural disasters, pandemics, wealth distribution, are all described by these type of heavy-tail distributions. And you're like, well, what is a heavy-tail distribution? And the basic, and there are much, much more formal definitions of this, but the basic concept is that if you have a distribution, let me find the right, I'll do it over here, I guess. No, I've already used that one. If I have a distribution, if I have, say, exponential to minus x, or d, right? You know, it's the same as e to the minus d, right? This is sort of the cutoff line between what are called heavy tail and light tail distributions. So if for large values of d, the numbers, the probabilities are below, well below this, we call a light tail distribution. So, for instance, if we had e to the minus d squared, right? That's just our normal distribution, or Poisson distribution, or almost every single distribution you have ever studied is a light tail distribution. Likewise, if it drops off more slowly than that, right? If the distribution is above this, the exponential, it's what we call a heavy tail distribution. And there's a fantastic book by Adam Weirman, first book. It's an accessible book on this topic, which I encourage you to look at. He's a professor at Caltech. Did a wonderful job of sort of making this accessible. These distributions are not unusual. They're very common. They're sometimes treated as sort of, oh, this is sort of very weird. They're very common. And in fact, a way to think about them is that light-tailed distributions, normal distributions, Gaussian distributions, Poisson distributions, are a natural result of additive random processes. So I have random numbers, and I just keep adding them together. I get things that look like light-tailed distributions. Likewise, heavy-tailed distributions are a natural result of multiplicative random properties, right? The most obvious one is the interest rates or your return you get on your investment, right? If you say I get 5% return, means it's multiplied. It's not I'm getting 5% on just the principal. It's like every year it compounds, and so that becomes more of a heavy tail distribution. And that's why wealth distribution tends to be a heavy tail process, right? Sometimes sometimes this is called the 80-20 law, right? Like historically, 80% of the wealth is in 20% of the population, right? Those kinds of things. So these are very important, right? I encourage people to explore them. There's a tremendously interesting area of research as these become more important. It's certainly something that we look at very closely and try and understand. Unfortunately, the mathematics of this, we have some challenges to overcome, because if I want to do a moment like computing, so integral of d to the minus alpha, right? I guess dd, I apologize, that was poor choice there. But where alpha is sort of greater than 1, I can integrate that. I will get a number, right? So it is a distribution. It is finite. However, if I try and compute any higher order moments, like the mean, that integral does not converge. It will go to infinity, right? And depending on what alpha is. So you have a very limited number of what are called moments. And a lot of the statistical properties that you see, and you'll often, if you read it in the textbook in the beginning there, it'll say this is for independent, identically distributed things that obey the central limit theorem, which means it has all its moments, which light-tailed distributions do, which is one of the reasons we like to study them, is because they are so well behaved. Not the first time in mathematics that we tend to focus on very well-behaved functions, even if they are not the things that are representative of what's going on in the world. And so certainly this is a very interesting topic that we're doing a lot of work on. So someone asked about extreme things. Let's see here. Now, why don't we talk a little bit more about bringing in some of the machine learning elements of this, okay? So one way to think about this is, we have, this, let's call this the Venn diagram of all of AI, right? And then as much as my computer science colleagues would like to say AI is more than machine learning, this is machine learning. It's pretty much all of AI. And then if I could make it even closer, I would, but I can't. But just assume this is almost epsilon width. This is deep neural networks. A great story, and I encourage you to go to OCW, and there's an introduction to AI course there, and the professor, who has since passed, gives a great talk. He's giving the lecture on deep neural networks. And sometime around 2008, 2010, there's a debate at MIT about whether we should even still teach neural networks. We've been studying them since the 50s, right? In fact, the computers that we built at Lincoln Laboratory is one of the first places that people ever worked on neural networks. And like, okay, this is an obvious, kind of like we think how the brain works. We should be able to solve these AI problems. And people had spent, you remember, you go from 1950 to 2010, people had spent their entire careers trying to make neural networks work. and they had failed. It was a complete failure at that point. And there was a serious debate, should we just drop neural networks altogether from the Intro to AI course? And in the end, they're like, nah, because people should know about this so they don't go and reproduce these mistakes, right? It's a rare instance, right? And then 2012, everything changes. And it's okay because, and the story I like to tell is that we had studied neural networks of sort of a certain scale over and over and over again, like relatively small neural networks, and we just couldn't get them to do anything really that useful. And then some researchers who've since won the Turing Award, quite deservedly so, said, you just need to go bigger. And I kind of, the analogy is like, there's this food, and if you eat a little bit of it, it makes you sick. But if you eat a lot of it, it's going to be great, right? That usually doesn't work in science. Like a little bit bad, but a lot really good, right? So they discovered if they just made these neural networks much, much bigger and used advanced computing and use a lot more data, that all of a sudden, it worked. Just a big example would be computer vision. In 2008, people who were computer vision researchers, like, you might as well say you were looking for the Holy Grail, right? It's like, yeah, we'd been working on it for 50 years. And then 4 years later, it just works, right? Computers can see. And now we consider that like every single time we take a picture, it's like, how do you get the computer vision to stop? Right? I don't want it to identify. I don't want it to crop the thing and give me it's like I have to stop the computer from doing the computer vision like all the time, right? Which is pretty impressive, right? And so let's talk a little bit about these deep neural networks and how they fit into this mathematics. So, I'm going to draw a simple neural network here, right? Very simple neural network. And we're going to call this the input feature vector, which I'm going to call y0. And then the output category, which we'll call yl. And these are each layers, right? So we have our neural, this is a very simple neural network, but it could have as many layers you want. And there's connections between them, right? And then the inputs go in some way, like that. And they go out. And each of these links contains a value, which is called a weight. And the basic idea is I give you some vector of information. Let's say it's a picture of a cat, right? So that's just a picture. It's just a sequence of numbers that are the colors in your picture. We unroll it into one big long vector. So even if it's a two-dimensional picture, we unroll it into one big vector. That's sometimes people confuse that. But yeah, our input vector is just a big vector representing one instance of the input data. And then it goes through this system. The values of that thing get multiplied. And then here are the categories, right? And one of these categories is cat, and the other is dog, right? And the hope is that when we put in a picture of a cat, that these weights have been set such that the score of cat is the highest, right? That's kind of the theory, right? Now, this can be represented as an equation, right? And so this is the DNN equation, which is essentially the value of the next layer. So YL plus 1 equals, we have this function h, which is just a nonlinear function. And then we have W of L, Y of L, plus B of L. And so Y and B are vectors, right? And W is essentially an adjacency matrix or a weight matrix, which connects one layer to the next. And this is the deep neural net equation. This is the whole thing, right? your colleagues are off in Silicon Valley saying they're DNN architects. They are just messing with this equation. Now, it's a testament to the fact that although this works, we do not know why, which is why your friends have jobs, right? Because they sit there and like, well, maybe I need to double the number of neurons here, or maybe I need more layers, or I'll tweak this. Like it's a trial and error thing. And we do now try and use AIs to kind of guide us through this process too. And these things get really, really big. So for instance, like ChatGPT, right? This thing will have billions of weights in it, right? And thousands of layers. The one thing we have learned in this space with DNNs is bigger is better, but we don't know why, right? We really don't understand. So it's a tremendously interesting mathematical question as to why this equation works. And unlike, say, signal processing, like in signal processing, I can give you a description of what my sensor, like the data I get. I can give you a description of what I want to find, the signal that I want to find. And then there's a bunch of mathematical principles that have been proven, like, and we can derive them based on, studies of, probability and other types of math that are highly predictive, right? I can tell you, given the data you have and what you're trying to find, like, either this is how much data you can have or this is how well you're going to find it. And the steps in between need to look like this, and they kind of, each one of them is sort of optimally built like that. This sort of a principled approach based on math allows us to do that, right? Which is really efficient. Otherwise, before they figured this out, it was all trial and error. Like, well, I'm going to try the wire here, put the wire there, maybe it'll work, maybe it won't. Of course, back then it was really wires, right, that you were doing this with. That's kind of where we are in the DNN space right now, is that we don't really have good theory for explaining this. And whoever figures that out, that's going to be pretty awesome, right? Now, this is not unusual, and it's very typical in applied math, right? When you go into an applied math class and we teach you an algorithm, like, okay, if you have this problem, we say, here's the problem you're trying to solve, and based on these principles, this is the optimal way to do it. And I think the misnomers, we somehow think that that's how we discovered the algorithm. It's not how we discovered the algorithm. Somebody else, an engineer, a scientist, an entrepreneur, an inventor, figured out that this, these kind of goes in and goes out seem to solve this problem. And then 2 to 4 decades later, mathematicians figured out the why. So that's kind of where we are. We're in this sometime in the next 20, 30 years, someone's going to figure out why this equation works, and then we'll be able to develop these things in a more principled manner. But right now, it's pretty much trial and error and throw more computing at the problem. All right, so I think I covered that question. And then, what are the limits of AI machine learning? So, right now, the limits are based on the computer chips and how fast they can go through this equation. And in particular, the algorithm we have for finding these weights, which is sometimes called training. The process of putting in a feature into a neural network and getting a result is called inference, and the process of finding what these weights are is called training. And the way we do it is not that sophisticated. We essentially set all our weights at random, right? And then we go and bring in a whole bunch of data for which we have known categories. So a lot of cat pictures, a lot of dog pictures, a lot of other examples, millions and millions, billions of examples. And we run them through and see the scores we get. And we average those scores up, and we take the difference of those scores from what it should be. And then using those differences, we essentially would do what's called gradient descent. We just essentially use those differences, like, okay, we see an error here, and we use that to tweak the weights. And then when we tweak these weights, and then we use those differences to tweak the other weights, et cetera, et cetera. It's called backpropagation, which is sort of a halfway point between numerical differentiation and traditional symbolic differentiation. You're kind of doing a little bit of both, right? And that was a big discovery, figuring out how to do this. And you can look up backpropagation. It really is what made this even possible. But that process where you're tweaking these weights by about 0.01% per time you do this is very slow. And typically you'll have to do this 10,000 to 100,000 times to get something that will work. And so the computer power to do this can become a limiting factor, right? In fact, the computers that do this today consume a considerable amount of energy. It is now an actual global warming issue with the amount of carbon that's used to generate the power for these computers. And so as these neural networks have gotten even bigger and required even more computing power, right, the chips and how much they can do has become a limiting factor. Now, I'm very much involved in benchmarking activities and other activities that sort of try and set the envelopes and how do we evaluate and assess these types of things. And the typical way that the performance of these chips is assessed is how many of these operations, this is the heavy-duty part, this matrix multiply, right? So how fast can it do those matrix multiplies is kind of the base unit of computation. And you get credit, right? If you have, the latest chips can essentially do this at about 2 times or 3 times 10 to the 15 operations, so 3 petaflops, right? One chip, 3 petaflops, can do these types of operations today. But one of the most interesting properties of deep neural networks, which we do not understand why it works, right, is the fact that in general, once I've trained my neural network, I can drop about 90% of the lowest valued weights, and I will get the same results. Sometimes the performance even does better, like the accuracy, like its ability to see cats and dogs goes up. We have no idea why, right? This is very suspicious, right? So some of the chips start doing that, take that into account, that you're going to what's called prune or sparsify these neural networks. And that brings up a very interesting measurement benchmarking question. Do you get credit for work that you did not do? I think we all like to get credit for work we not do, right? So sometimes people say yes. And in fact, in some of the specifications of some of these chips, it will say, it will double the number of things and say these are sparse operations. Because we're taking account of the fact that we can see that there's a 0 here, and so we're just not going to do that, right? So that's interesting. That's an interesting game to play. And I'll say one reason we might like that game is because our human brains are incredibly sparse, right? We have about 100 billion neurons with about 100 trillion connections, so about 1,000 connections per neuron. So that's like a sparsity of 1,000 divided by 100 billion, right? So very, very sparse, right? And if you give our brains credit for all the work it is not doing, right, we will never build a computer that will be more powerful than that, right? So in a certain sense, and many people believe that sparsity is the only sort of path forward to continuing this game, and there are a lot of people working on those types of problems. In fact, we've set up benchmarks for doing this that will allow people to kind of do things with trillions of weights, although most of them don't exist. So when people ask, what are the limits of AI and where does it compare to the human brain? A lot of it depends on that question, right? How important is sparsity? The human brain is extremely sparse, and if you also the fact that we're really energy efficient, I mean, we're 70 watts, right? One of these chips is like 500, right? So we don't know the answer to that. It kind of really depends on which way this question goes. There might be things that the human brain will always be relatively better than just from an efficiency perspective. Now, the great thing about these computers is they don't get tired, right? And that was one of the big innovations that we discovered when we first got neural networks to identify cats and dogs in pictures, is that prior methods were producing error rates about 25% on these tests, and humans were about 5% error rates. And so these neural networks just kind of got that number down by a factor of 5 to where it was comparable to humans. And you think, well, doesn't it need to be way better? No, because the computers don't get tired, right? So now you could just have computers just go and do this task once it achieved. And we didn't really realize at the time, like, oh, if we just match human performance, we don't need to exceed human performance on a certain set of tasks. Now it can be given to a computer instead of a human, and then it can become, we can scale it out and do many more things. We didn't really know that. So part of the success was, not only did we not know that DNNs, if we just made them bigger, they would work, but that we were only about a factor of 5 away from something that was commercially very interesting to be able to do, right? And so that's kind of just the way innovation goes. It's kind of two things. It's like, technology makes things better. The business conditions change, so it turns out you're closer to success than you thought. And then those two lines cross, and then sort of magic happens. So I think that addresses that question. And I think I've also addressed, like, where do we see big data going in the future? A lot of it is, I think, to me, the really interesting questions is, why do deep neural networks work at all mathematically? Like, that is a very wide open question. And all I know is that someone my age is not going to come up with the answer. It's going to be someone more like one of you that's going to figure that out. These heavy tail distributions, again, which we have not studied very much, is not very taught. Again, this seems to be very important to many of the most important problems to deal with. And then from a computation perspective, this sparsity question, like, what is that about, right? And is it really the case that as we make deep neural networks sparser, is there a way we can make them better? There are also very interesting things going on, though, where people are making neurons much smarter and therefore shrink them quite dramatically, and those could have game-changing effects. There's a lot of it. Now that the computational limits have reached such enormous costs, there is a lot more energy and effort being put into how do we make this, how do we solve these problems using theoretical concepts. So I think it's a really great time to be thinking about mathematics and theory of these problems, because they've reached limits where we really need a better theory and better theories to solve them. And so it's a really wonderful time to do this kind of work. So with that, I will then hand it over to Hayden. I don't think I left him much time. I'm so sorry, Hayden. But I guess impressions, did this work? Was this an interesting way to go about this? Never been done before, as far as I know. So, okay, yeah. People feel like they got their questions answered, right?